But I will say we are striving to be a global streaming video company for TVs and movies. And today we're in 36 million subscribers, more than 40 countries. Netherlands coming later this year. And if you haven't seen this stat, it kind of still freaks me out. We are accounting for, in North America, about 33% of total internet traffic during peak hours. And today we're on about 1,000 different device types. So that includes the suite of iOS and all the common ones that you would expect, but all the different TVs and Blu-ray players, and pretty much if you have a device that's capable of streaming video, it's got Netflix on it, maybe with a couple exceptions. So how did all this start? Back in 2007, we had this idea of maybe we should start streaming instead of just delivering discs by mail. So that's when we started the streaming business. And shortly after that, we launched this API. So I'm going to call this the one-size-fits-all API. It's basically a traditional REST API. It exposes a bunch of metadata that you can access around both the disk world and the streaming world. And it exposes data so that 1,000 flowers out there in the world can plant seeds and bloom all kinds of magic, all kinds of development. Basically, it's kind of like an outsourced development model. That's what we're striving for. And at the time, the API was focused strictly on that. 100% of all the traffic to the API was coming in from those third-party public developers, not Netflix employees. And they developed a whole host of things. And these are some examples: Feedflix, and Flixster, and Rotten Tomatoes, and all kinds of different implementations. Jazz, for example, is a matchmaking site. They wanted to share each other's recently watched to say, "Oh, you watched that too." So all kinds of very interesting mashups here. But streaming really started to take off after a little while. And what we saw was we added more and more devices, and more users came and cared about the streaming. We still had the DVD business at the time, but you could see the trend going towards streaming. And eventually, like I said, we're at 1,000 different devices. And the API program became, how do we support those devices? We still have those flowers in the background here. That's still part of the charter, but by and large, devices really took over. And that manifests itself in the traffic as well. So today, it's much more like this. In fact, if I were to show you the actual representation, you wouldn't even see this red line, because the public API traffic represents less than 0.1% of the total API traffic. So a dramatic shift in the overall charter for the API, and it's all about the streaming product. So the streaming aspects, or the streaming product now has 3 primary aspects that we're targeting here. Today the API supports discovery, sign up, and streaming. Discovery is basically browsing around, looking for titles that you want to watch, learning about them, adding them to your queue, rating them, all the interactions with the metadata. Member sign-up is what you would expect. It's how you become a member to the system. And then streaming is when you find something that you want, you press the button, that is where you're going to the video. So actually today, we're in process of getting the streaming supported by the API. All the other components are fronted by the API. So I want to talk now about the organization that we set up as this transition was happening. And I think this is actually the most important aspect of our ability to scale this system. So organization structure. Before we really endeavored into this, we had somewhat of a monolithic app. We had a single database or a set of databases in a data center, and it was basically that is the system, the application sitting on top of that. When we started moving to the cloud, we really started to distribute things out and create more of a distributed model, both in terms of the dependent services as well as the engineering that goes around the distribution pipe and the applications on the client devices. So I like to think of it as an hourglass model. What I mean by that is at the top, there are many, many devices. I already said 1,000 different devices. At the bottom, there are now dozens of different services that are doing very specific things. So what we set up our engineering organization to do is we might have something like a member database where we have information about our subscribers. There's a service that is designed specifically to handle that problem set and to engineer that and to innovate around that and push the envelope as much as possible. There's another system around ratings. There's another system around recommendations, and there are dozens and dozens of these. They're all specialized, and basically what we're doing is we're exposing services to each other so we can consume it, pass it around. It's very much an SOA model. And at the center of all this is the API, right? So the API is the broker of all this data. API does not actually host any data. What we do is we handle requests from devices, and we translate them into requests that we make outbound to get the data from all those dependent services. And then we pass it back on to the corresponding devices. So the reason this is really important is it creates a horizontally scalable situation. So we can add new services, we can add new devices in such a way that it doesn't really impact the overall architecture of what we're doing. Basically what we do is we would add a service, the API will then incorporate into its interfaces, get that data available, and then expose endpoints or other methods of getting that data to the UI views. So it allows for that massive horizontal scaling, and I think the organization grew in the last year, or last couple of years since I've been there, by 400 or 500 people, and those people correspond to services, and as those services ramp up, it's pretty easy to add them on. The other key aspect of this is that we have a culture that enables us to move nimbly. So if you haven't read this culture slide, I highly encourage it. There's the URL. It's basically describing our freedom and responsibility culture, which in essence is we build an engineering organization that allows people to go and build whatever they need to build, trust them to make great decisions. If they don't make great decisions, then we change that situation. But basically put people in the position of doing what's best and trusting them with everything. So, I'm going to talk a little bit about those systems that all those engineers are supporting. And I want to talk a little bit about resiliency first, because if you have a distributed system, like what we have, with dozens and dozens of services, you end up with a graph like this, right? So this is an output from App Dynamics. You see a couple of people looking upset. This is actually, it's quite complicated. Nobody actually uses this to interpret anything. It's really representing how complicated this system is. And if you think about it, today the Netflix API does about 2 billion transactions a day. We have direct interfaces to 30 different dependent services. And to those services, we are making outbound calls about 14 billion per day. So a lot of traffic piping through. And 0 of them have an SLA of 100%. Right? So with that, you have some computations here. 99.99%, so 4.9 SLA. If you assume that across all 30 of those services, you end up with roughly 99.7% SLA.
What's SLA?
Service level agreement. SLA basically is a service is going to say, I'm going to provide this amount of uptime and these latencies. And if you don't meet those, then you're breaching the SLA. So if you assume that across the suite of those, 99.7% SLA for the entire fleet, it basically translates into 6 million failures per day. Or you can also think of it as about 2 hours per month of downtime. And that's, by the way, assuming 4 nines, right, which is really, it's a good benchmark, but it's not always easy to achieve. So if you put it into, I guess, a looser model, 99.939s, then really what you're talking about is basically a day of downtime per month, and that's totally unacceptable, right? So what we did, by the way, that's unacceptable. So what we did is we looked at our organization, we saw this opportunity to improve the failure rates for the customers, right? Insulate them from those failures, even though the services underneath them are failing. So when we look at this, basically if we have a scenario where one of our services, this is the member database, if that fails, this is how it was when I first started at Netflix, the API would fail, and then everything would fail. And then we have a lot of unhappy people, including myself, many calls on a Sunday night dealing with this. So my team, what we did is we built this service called Hystrix, and you're going to see this logo down here throughout the slides. It's basically, we have open sourced this, and it's available for anyone to use. And Hystrix also comes with this dashboard, and this is a very complicated view. I'm going to walk you through it. But in essence, what this dashboard is representing is each one of these nodes is a single service, one of those back-end 30 services that we call. In fact, it's actually more granular than that. It's not just a service, it's an interface, so there are probably 80 or 90 of these. And so what this looks like is basically, it's a real-time flow. So basically every couple seconds, we're seeing traffic flow through this. And it's kind of hard to see. Can you see that box up there? Right. Basically what's happening is the last 10 seconds, it's showing you a view of just the overall volume. It's a visual indicator of how much traffic is coming through this particular service. And if you go back, you can see there are different sizes here. So different services are seeing different traffic from us as we go. This blue line is a 2-minute running graph of basically what the call pattern is looking like. So you can see that it's changing over time. And what you can see there is if there is some sort of failure or issue, you'll see a dip. Or if there's a thundering herd, you'll see a spike, that kind of stuff. And then these numbers over here all represent actual call states. So successful requests, latent requests, latent basically meaning it's delivering, but it's going slower than we would expect. Short-circuited, which basically means we're delivering a fallback state. Also delivering fallbacks, but these are timeouts. And basically, thread pools, queues, and things like that, also fallbacks. And then exceptions, also fallbacks. And the key to this is the exception error rate. Each service has the ability to have a specific percentage that if we exceed a percentage of basically failed states, anything that's going to potentially deliver a fallback, we keep track of that percentage here. And if we hit a threshold, we toggle the circuit. Toggling the circuit means we're going to, if it's unhealthy, let's say it exceeds that percentage, we're going to basically turn that service off and say, you're dead to me. I'm just going to do something else. And that something else ideally would be deliver some fallback state that is useful to the customer. So an example of that is if we have our recommendation service and the recommendation service is down, what we would try to do is maybe deliver popular titles. It doesn't have to be recommendations. That's really hard to get if the service is down. But we'll basically say, you're dead to me. I'm going to deliver you this other stuff instead. Now, some services, we can't do that for a variety of reasons. So the default in those scenarios will be fast 500. And basically what that means is, rather than keep trying or waiting for the response, what we're going to do is we're going to say, again, you're dead to me, and I'm just going to assume that you're dead and hand it off to the corresponding requester, rather than letting it queue up and create a load shedding problem and then ultimately tip over. So that's what that circuit does. And ultimately what's going to happen is over time, the circuit will be checked automatically and say, how am I doing now? Am I doing okay? If so, I'll turn the circuit back on and let real traffic go through. And it's always in this state of evaluating the health of that.
Is that a literal 500 or is that a 503?
It's a 5xx, depending on the situation.
You're doing failure masking then, partial failure?
What do you mean?
You're masking the error by providing some data.
Yeah, it's an installation layer, right? So we're isolating the failure, saying there's a failure here, pretend you don't exist, and we're going to do something else over here.
And then do you have failover capability as well?
The API team, or the front door, right? Yeah.
Yeah, with these numbers, from where do you start to care about the error rate?
The global error rate, or for a service?
For example, I mean, it just shows one full digit, and from where.
Which number? This, the percentage?
The error rate. Percentage, yeah.
Yeah, so the percentage, each service is going to have a different percentage that we care about. So we basically tune that over time. As we learn more about the thresholds, we're going to adjust those percentages, and it's on a service-by-service basis. Okay, so other details on this chart. Basically, this is just key information, host counts, and cluster sizes, and things like that, as well as baseline SLAs. What are we actually delivering in terms of our latencies? So, with that in mind, any other questions about the circuit breaker dashboard or anything like that? It's all open source. So if we go back to this view, we assume that that member database goes down again. Basically what we're doing is we're snapping that. Rather than having that skull go back up to the API, we're snapping it. We're calling a fallback. So, all right, I'm going to move on. So other aspects of
I was just wondering, in dire situations, have you had a situation where the callback itself, is that a network service or is that just kind of like a hard coded?
So depends. The question is, if the fallback, where did the fallbacks live, and have we had issues with that? So some cases the fallback is within our code, and we're basically just delivering the fast 500 because there is no fallback. But our SOA model, or pseudo SOA model, is basically there's a service over here, but that service also creates a client jar. And so all of those dependencies that we pull in, we're actually, in most cases, pulling in their client jars. And their client jars know how to interface with the services through REST or whatever means that they have. But also, if we turn off that circuit, there's usually a fallback state inside the client. So it's inside our container. So it depends on the situation, but that's often the case. Okay, so infrastructure, other aspects of scaling systems. So if you're not aware, basically the entire streaming application is running out of EC2, Amazon Web Services. And this is a key fundamental shift for us, primarily because rather than spending time in rooms like these, where we're dealing with hardware, system patches, and whatever else, we end up building tools like this, also an open source tool. It's called Asgard. And what Asgard is it's a mechanism that allows us to manage our EC2 instances and launch them in various clusters or regions and do all of this interfacing. So we're not dealing with servers, and what we're doing is we're writing apps to access the AWS APIs and do things for us. So instead of going in the room and dealing with all this hardware, we're pushing buttons on an interface that we create. Another thing that we're taking advantage of out of AWS is auto-scaling. And so this is like a typical couple days for us. And if you have a data center, basically what you need to do is you need to build your system to that red line or somewhere around that. So basically you need to be able to handle a spike in traffic as well as have some buffer room in case there's growing traffic and whatever else. And so you're basically spending all this money for most of the time you don't need that capacity. So for us, we're taking advantage of auto-scaling. And so basically our server counts are ebbing and flowing as our traffic is. And we've spent a lot of time on tuning those algorithms and touching the AWS APIs at appropriate times and doing various things so that we are really mimicking what the traffic is going to do, and in some cases predicting and getting ahead of it. So this is a key part of maintaining the resiliency and the scale. And, as the system grows traffic over time, we don't have to worry about adding capacity. It's just going to naturally happen. So now,
sorry, for auto scaling, are you using business metrics like number of posts or things like that, or response times, or are you using server level metrics, CPU, memory, to do the scaling?
A lot of teams are using load average, some are using RPS, those kinds of things. We do a hybrid of some of that stuff, and we're in transition. But usually server side metrics.
So for the AWS, is it 100% of the apps? Like you don't have maintain like a steady state bare metal with overflow to AWS? Or?
There are some legacy components that are still in the data center, but you can pretty much assume the entire app is running out of AWS, minus some of those legacy components. But those legacy components are really just kind of small backbone things, and we're deprecating those.
And then can I get a follow-up question?
Yeah.
So I've always been kind of the rule of thumb is AWS is great up to a point, and then it gets really expensive. Right? You guys are huge. I'm sure you've done the math. Like, what was the tipping point for you, or what the decisions were to say, yeah, AWS staying there is more cost effective than building a DevOps or all that stuff.
Right. So the question is cost of AWS and how do we justify that? And obviously, I'm not going to get into the numbers, but what I will say is we view it as a non-differentiating effort for us. So why would we spend our time and energy on building up that infrastructure? We can leverage them and apply all of those energies to things that we really care about. It's really an opportunity cost type of calculation. And another way to think about it, I pulled this slide from my deck, but I have a slide that basically represents the API traffic growth over time, and in a 2-year span, it grew by 70 times. And so, not trivial numbers either. It went from like 600 million requests per month to 60 billion, or, 60 billion per month, something like that. And if you're trying to grow your system to scale at a 70-time rate over a 2-year span, how much time and energy and money are you putting into that? Or you can just leverage someone else's infrastructure and they're capable of doing it. Okay. So we've established all of these mechanisms that help with preventing failures, resiliency, and all those other things, and scaling the system. So the next natural thing for us to do is force failures in production. And so another thing that we've open sourced is our Simian Army. People familiar with the Simian Army? Chaos Monkey and stuff like that. So what this is basically a fleet of monkeys that we've instituted to basically wreak havoc on our system. Chaos Monkey is the earliest one. In essence, what Chaos Monkey does is it runs around in production and periodically shoots a server in the head and kills it. And the idea is, well, we don't know what would happen if that server dies, so let's see, right? Let Chaos Monkey kind of do its thing. And if it breaks something, it's kind of in more of a controlled scenario. It's not happening in the middle of our peak hours. We're running Chaos Monkey at strategic times, and it'll take things down. And if actually we have a failure, well, everyone's around, we can respond to it and deal with it. So in addition to Chaos Monkey, we also have things like Latency Monkey. Latency Monkey is a tool that allows us to inject latency into our system and see how we handle. Like, are we really fast failing like we said we are? Are we delivering the fallbacks like we claim? We also have things like Chaos Calm, which basically takes down a region. So we have a lot of stuff going on. There's Conformity Monkey, which makes sure that our clusters are conformed to each other. It's pretty interesting, and basically what we're doing is we're saying, we don't know exactly how these systems are going to fail, so let's introduce things in an unpredictable way so that we can respond to them accordingly. So globally, deploying this system. That's another thing that we've been exercising over the last couple of years as we've been doing global. And again, AWS plays a key component of it. So these are the regions that we're in today, and the countries correspond to that. And being able to spin those up in AWS is actually a lot easier than flying people over to Europe and setting up data centers or whatever else. So that's part of the strategy as well. As we spin out in new regions, we can set up clusters in those corresponding regions. And along the way, we introduced this application called Zool. Anyone heard of Zool yet? Okay, so a couple. Also open sourced. And what Zool is basically the gatekeeper to our system. And every request coming in from the device hits Zool first, which is in essence doing, doing these things. It's handling multi-region resiliency, insights, stress testing, dynamic routing, all of those things. And the first thing that it does is evaluate that request, see what filters it needs to act on, how it needs to behave, and then it routes that request accordingly. And if things are going well, it's going to go to the API server, and then we're going to process what that request really means, and then we call those dependencies. So that's basically the chain. And Zool is, you can imagine, it is the single point of failure for the entire system. So we spend a lot of time trying to make that robust. And we also spend a lot of time trying to make it nimble. And so one of the things that we instituted there, and we'll talk more about this later, but we have this multi-tiered architecture for it, where it's basically a Java core that knows how to execute on a range of business logic, or not business logic, but filter logic, basically. And then we have Groovy tier sitting on top of that, and we can dynamically throw new filters into the system and say, this device is creating problems, or this specific device is creating problems, let's 404 it. And just do that on the fly and throw it up, and it's going to cascade out to all the servers. So there is a component of this is our single point of failure, but it's also our single point where we can capture things and do all kinds of rerouting or whatever else we need to. Another thing that we used Zool for was what we call isthmus. And in essence, what this allows us to do is route traffic across regions. So if someone comes in from US West, and for some reason US West is down or whatever else, we can redirect that traffic over to a different region. And so isthmus is the layer that allows us to push things around, and that's all about the Zool. Okay, so moving on to devices. I think a lot of companies are focused on, at least out of the gate, these two platforms that you're shooting for. And if you have a handful of devices that you're shooting for, the world's a little more simple than the 1,000 that we have. So supporting the 1,000 devices has a different kind of scaling problem, and it manifests itself in a very different way. So I'm going to talk through some of the differences that cause us to think about these problems differently, and then some of our solutions to that with the API. So first, screen real estate. There's just a fundamental difference between what you can see on an iPhone and on a smart TV, or an Xbox, or whatever else. And that actually changes the dynamic of what data that you want. So an iPhone, much smaller screen, fewer titles on it, fewer metadata fields that you're going to expose. TV, a lot more. Same with an iPad, it's just a different form factor, different data. And that actually influences things, because if you go back to earlier where I talked about the one-size-fits-all API model, it's basically treating them all identically. And they're not identical. They actually have significant differences. But treating them identically makes them fight against the API, or basically be not as efficient as they could be. This is one factor that we considered when we were looking at scaling the devices. The controller. So if you think about the Apple TV LRUD controller, it's pretty simple. You can go right, left, up, down, and you can have somewhat of a controlled experience in getting and delivering metadata. So you can imagine a scenario where you have 5 titles in front of you, and you scroll to the right, and you go and fetch more titles that you populate. But an iPad, where you're holding it and you swipe it and you see title, and they just fly by you, you have to pre-populate. You need to have that different interaction model to do that. And if you're doing it in this one-size-fits-all world, it's highly granular, but you're basically treating them the same, and the interaction model is very different. And then technical capabilities. What's the memory constraints on a given device, the CPU, all of those things. So those are going to influence how much data the device can hold in memory and process in real time, or how much do I need to fetch, those kinds of things. And then ultimately, when you have this many devices, you have lots of requests. Right? On this chart, it's like Jira requests. Shout out to Atlassian. It's not API requests. So basically what we have is we have many teams asking us for feature changes. And that either translates into a funnel effect, where we basically have to distill them down and defer work, or it has us rushing through things, and then we're doing spaghetti code, and we end up introducing all kinds of future problems into our system. So this is actually, I think, was one of the key drivers in having us do introspection. And ultimately that turns into how do we scale the development of all this. So I'm going to talk a little bit about how that translates into things that we actually did to fix this. And by the way, lots of companies do this. Companies introduce orchestration layers and basically allow different systems to merge data, and we try to solve this through efficiencies at an orchestration layer. And some of those would be, OData, RESTly, RQL, etc. We took a different approach to solve the same problem. And our approach, I like to boil it down to comparing that one-size-fits-all API, which I consider to be like a resource-based API, and compare it to our experience-based API. We're going to talk a little bit about what that means. So in our one-size-fits-all API, the resource-based, we have a series of endpoints that can be called, and they're very granular. I want to get the ratings for this user. I want to get the queue for this user. I want to get the metadata for this title. And you can see that there's going to be a lot of individual requests to create an experience. And this is basically what it looks like. For this example, you have a PS3 making a bunch of calls. This is, you can imagine as you start up your PS3, it makes a bunch of calls into the REST API, and then this REST API calls will go to dependent services and gather the data. And all of these are happening across HTTP, which is the most expensive route you can take. And some of the divides here, I think it's important to note that in this model, the network border is the divide between client and server. It's also a divide between where the user interface renders, all the user interface work is happening there, and the data gathering, formatting, and delivery is happening on the server. And ultimately it works, right? This is what we use to launch a lot of devices. Looks pretty, right? Ultimately we were able to assemble this. problem with it is I like to equate this to pointillism. Right? So you can put a lot of dots on a painting, and as you assemble enough dots, it actually looks like a pretty painting, but it's not particularly efficient. It's fine for art. It's not great for computer science. Right? So our experience-based model is more about what do we need in order to create this experience. Let's not worry about the granular resources. Let's worry about the experience. And so in this case, you might say, I want the PS3 home screen. And in this model, it looks fundamentally different. One HTTP request going across the wire, hitting this Groovy layer that I mentioned earlier. I'll talk about that in a second. That Groovy layer is, in essence, built by the UI teams. And it makes calls back into the API where we expose Java methods. It's no longer a REST-based interaction. It's Java methods. And those Java methods will figure out what they're looking for, go down to dependent services, gather all that stuff, hand it off to the Groovy script, and the Groovy script will return whatever it wants to the UI. So it's important to note that we also open sourced a tool here called RxJava. And RxJava is basically what we're using to make this whole process much more efficient through concurrency and callbacks. And basically, it allows us to do all of this in a highly concurrent manner because we already have everything that we need. We can not only minimize the number of HTTP calls, but we can take all of those backend requests, deserialize them, go get all the things at once, and then hand them off at the same time. So, going back to this bifurcation here, the client code is still on the client side, on the other side of HTTP. Then the client adapter code is what I'm calling the Groovy scripts. And that's really, they're writing the client code, the Groovy. And what they're doing in real time, we deploy our OR files, right, which is the Java side, but in real time, totally independent of our pushes, they're writing their scripts and pushing them out, and they cascade into our entire farm. And what happens there is those Groovy scripts, they're loaded into memory, pile into the JVM, and they operate as Java at that point. So what that does, going back to that funnel model, it decouples their delivery, their continued innovation from requesting things from us. As long as that data is available in our Java APIs, they can innovate as fast as they want. And in this breakout, user interface rendering still happens in the device. Data formatting and delivery is now on the server, but in this adapter code. So the UI teams are responsible for that, and the data gathering is on the server side. And the important aspect of this is that the data formatting and delivery, previously in the one-size-fits-all world, the server team would define the rules. And you have 1,000 different devices, they all have different cares, and so they're basically giving us all these requests on how we can change things. We got ourselves out of that business basically and said, all right, we won't give you the data, now you do the formatting and delivery, which is the nuanced part, the thing that's constantly evolving. We got ourselves out of that business and put them in that business. And the other important aspect of that is as the Groovy scripts change, the UI changes, so they're tightly bound to each other. So rather than us changing in the REST world and then they change their corresponding interactions, they have total control of that entire interaction, as long as the data is there, of course. So I kind of think of this more as a photograph. Right? Instead of the pointillism where we're assembling a bunch of dots and painting this picture, we're basically taking a photograph and pushing it up. Any questions about that? Yeah?
So, if you weren't in the business of making your own clients, I would imagine that kind of nuance really would work, right?
Absolutely. I think there is a recipe for when this is applicable. And as you said, pretty much all of the UIs for all of our Netflix branded devices that stream video are built by Netflix engineers who are down the hall. I actually published a blog post detailing the recipe that I think needs to happen. I don't remember all the tenets, but it's on programmable web if you want to check it out. But I think that some of the examples would be a small team of developers who consume this. They're very close to you. They have incentives to have optimized models, those kinds of things. It does not work for a public API, and I would never open this up to the public. I would never have random people in the world throwing Groovy scripts into my JVM. Okay, so I want to talk a little bit about testing. Are you doing okay on time?
Yep.
Okay. So, remember this? hard to forget. Things are very complicated. There are lots and lots of change happening all the time. And if we were to try and keep up with all that change with all these tests, it's just not going to scale. It's not going to work. So our philosophy around testing is act fast, react fast. What I mean by that is we do tests. I'm not trying to say we don't do those things. We definitely do. But we're not trying to make it bulletproof. What we're trying to do is have sanity checks, making sure that things are stable, smoke screen for certain types of issues. And if it looks good, we push it out. Now, it sounds risky, but the way that we push it out, I'm going to talk about those two key components to this, is very important. And it actually is giving us much more data than our testing suite could. So we have two things called canary and red flag deployments. I'm going to talk a little bit about how they interact with each other. So you can imagine we have a fleet of servers that are handling production code today. All that traffic is coming in. And we have new code that we want to deploy. So we do our suite of testing, right? We do all that automation. And by the way, everything I'm talking about here is basically an automated pipeline. So the commit happens, it's going to do the test, it's going to then trigger the following events. First of which is we're going to basically build an AMI and prepare something, push it out on a canary. And this canary is basically, one or a small handful of instances across hundreds. And we're seeing real traffic coming through to this canary instance. And we can do canary analysis, basically health checks and a range of other things to evaluate, is this canary as healthy or more healthy than the fleet of servers that are currently out there? And if so, well, I guess if not, we'll yank it down, we'll fix it, we'll do all this stuff, and then we'll push another canary out. And then, okay, now it's good. So if it looks good, then what we'll do is we'll pull down the canary, and we'll push up the new code in a brand new cluster in AWS. And this, again, is the power of AWS. We can add and kill servers and not worry about that.
You have specific times when you do that?
Yes, and it's the automation kind of detects. The question is, do we have different times when we do these deploys? And the automation that we have is sensitive to peak hours, for example, in a given region. So EU will defer a deployment because we know they're in peak, but we might push it in the US first. Ultimately, the pipeline should mature over time such that we don't care when we deploy it. It should be risk-free and easily rolled back and whatever else. And we're pretty close to that. So if it looks good, the canary will launch this black cluster and we'll point traffic over to it. But sometimes, with the increased load and just the variability of having more requests come through, we might still see an error. So if that happens, it's a quick switch over to point to the old cluster, and we'll yank down that, fix stuff, put another canary. And then hopefully that canary looks good again, and sometimes this does happen. But if the canary looks good again, we will launch the new code again in the black cluster, toggle it again. If that looks good, until the old one. Yeah.
So do you do the canary for every type of change, or some changes you take a risk, or?
Yes, I would say for the most part we do canaries for code changes.
Okay.
We might have variable durations that we want it up there for, depending on how big the change is.
Right.
In some cases we might bundle changes and whatever else. There are certain kinds of changes, like fast config changes, that we don't have canaries for. We have a different route of doing all of that stuff. So there are some mechanisms of affecting production where you're not doing this. Okay, so I talked a lot about a whole suite of things, and among them were our open source. So I thought I'd mention we're on GitHub/Netflix. I think there are about 34 open source projects. I mentioned maybe a dozen of them, including the Simian army, which probably accounts for 8 or so. So yeah, feel free to go check it out. And that's all I got.
Awesome, thank you so much. So you guys kind of asked questions throughout, but we'll take a couple different questions. I have our brand new community manager, Mary, here that's going to pass the microphone around. So if a couple of you have questions, just put your hand up. Anyone? Kind of ask questions throughout, so I'm not sure that you do. Okay, then. Well, and oh, we have one here.
How do you guys determine what part of the system is scale at what point? Do you guys have some internal analytics that you guys run to decide what the system is scaling? Or do you guys just have an idea around what you guys are trying to build and how the roadmap decides what are they looking at scaling?
So a lot of the scaling is done through auto scaling or automation. There are components, like if we're launching a region or if we're launching a new feature that's exercising a different area of the system that otherwise wasn't exercised, we will do some capacity planning, which is humans sitting down and evaluating roughly what kind of lift are we expecting in that given service and how do we want to set our minimums and maximums in AWS to reflect that. So if, for example, we're expecting a 60% increase for that on launch, what we might do is lift it higher, give ourselves a buffer, but then settle in on some number. So it's usually capacity planning type of stuff.
I can talk loud.
Don't make her work that hard.
Yeah, she's coming.
Hi, so I've got actually two questions. The first one's about Chaos Monkey. I think that's one of the coolest names and coolest things ever. But what about data loss and then also relational databases? Does Chaos Monkey have anything to do with relational databases? I read before that you guys actually used to have your databases off of AWS, but it sounds like from your talk that that's not the case anymore.
Yeah, so there are different aspects of the system. By and large, we're using Cassandra in AWS. And Chaos Monkey, basically the way it's set up is that it runs around killing servers, whether it's a Cassandra server or an API server or whatever else, it's going to kill it unless it's opted out. So there are mechanisms to say, don't touch this. That would be very bad.
Databases never die.
Yeah, but it's a distributed database fleet, in which case killing one instance, which happens often, randomly. Why not take it out?
But not MySQL.
We do have some cases of MySQL. I don't recall where they are. There are some cases. I don't recall. Sorry.
So you built your application basically so for instance, let's say I'm logging in and the server that I just logged into wasn't able to make the connection. It just come back and asked me to log in again. Chaos Monkey, you made your code fault tolerant to that.
Yeah, hopefully it was actually insulate you from experiencing that, right? So through retries and all those other things, and basically your request will come from the device, hit us, we'll try and call the sign up or whatever else, and if that gives us a 500 and the circuit is healthy, then we'll try again on the server side and insulate you from that. Was that your question?
Yeah, totally. Thanks.
Making Mary work.
First week.
Do you have an example of a failed attempted scaling methods and some of this?
A failed attempt? What form of scale?
All right, thinking that you might have. Aside from that, I actually have another question about some of the circuit breakers that you have. Is it automatic in the sense that it will open that server, take that server out, and then is it automatic that server heals itself and then back or is that something?
Okay. So I'll give you an example of a failed scenario of scaling on our side, which is not about servers, because that doesn't happen as often. Although there are cases where we might scale things up, and actually that scaling up creates a thunder and curve effect where, because we've introduced more traffic, this actually is a somewhat common pattern. But if we are under provisioned, we add more servers, and in adding more servers, it unlocks the queue, and then all of that stuff comes flushing through, and then that tears down the system again. So we figured that out to some extent. There are scenarios where that still heals us. Another example where my team had a scaling issue, which is a server scaling issue, is we introduced that whole Groovy tier, and teams are ad hoc just throwing these scripts in there. What we didn't account for is how many scripts and endpoints they're going to dynamically create. And so as they started ramping up in their use, it was probably a couple dozen of total scripts, didn't really impact much. And then 1 month, one of the UI teams had a very different method by creating them, and it hockey stick straight up. And what that did was it occupied all this permgen space, and it hit our threshold and tore down the whole server. So that kind of sucked. With respect to your other question about circuit breakers, that is an automatic event. So once we hit a certain error rate, that given server is going to, or that given circuit is going to flip on. Basically consider that dead. Every once in a while check in and say, are you still dead? You're still dead. And if it's alive again, it'll flip itself back on.
So I just have one quick question. So you were talking about the canary and the black and the red. How many deploys do you guys do deploys daily, weekly? Is it just kind of whatever?
By you guys meaning my team?
Yes, your team.
So we are close to, if not daily, and some days we're doing multiple, and our aspiration is to have the potential to deploy at any time, multiple times a day. And so what we're doing today is, in a certain set of cases, a commit will happen by the developer, and it's going to launch that entire process. So the commit will basically say, let's build an AMI, let's launch an instance, let's test it, we'll hit it with all these tests. If that looks good, we'll launch a canary. If that looks good, we're going to roll it out to a given cluster. If that looks good, we're going to spit it out to all the regions, and then it's going to shut down all the old instances. That is an automated pipeline. We're trying to build more confidence around that, and as we do, we're getting more aggressive with the frequency of our deploys.
I'm related to that actually. Is how are you using new configuration management and build those AMIs automatically?
Python scripts. And some other tools that we have.
So keeping with the canary, I mean, if you have multiple deployments, even a day, do you have multiple canaries?
Well, I mean, usually it's sequential. Right? So we're not launching multiple deploys at the same time and then spinning up double the clusters. It's usually a sequence of we're going to go through this entire pipeline. When that pipeline is exhausted, if something else comes in on the tails, we'll trigger it again. But we're not going to run multiple at the same time. For my team. Other teams are doing their own sequencing as well.
One more question.
So, see, AWS got like so many different regions. So, how do you auto scale like in terms perspective of like, for example, Virginia is like over capacity from Amazon. So, how are you doing?
Yes, we have reservations in the regions that we care about, and so we know we have the capacity we need. So that's seldom an issue. But different regions have different capacity needs, and they're scaling. The auto scaling up and down is also going to be variable based on region and who's accessing it. The other thing that is a benefit for auto scaling is my team might be ramping down our instance count while another team needs more. And so we're actually able to re-provision the instances as we scale down for other purposes. Some of those purposes might be scheduled events to build a caching tier, which is highly computed algorithms. So we wait for a low point in our total AWS usage in order to trigger those kinds of events. So that's allowing us to leverage the downscaling.
Okay, actually, so we have one last question, so I'll toss it back over here.
So my question is regarding managing the complexity. So we have the layer of open source systems, like 100,000. And so if we get an issue in production, right, how do we manage that? How do we troubleshoot and figure out, okay, we have this open source causing this issue. Do we have any practice troubleshooting?
So a lot of it is all about tools. It's a very complex system, lots of different services, lots of instances. Something like the Histrix dashboard gives you an immediate indicator. So the API is at the very edge, and then we have a view into a good portion of the overall system. And if one of those turns red and goes to one state where there's a fallback, you see that. It's very apparent, very obvious, and you can say, okay, that
recommendation team, let's get them on the phone. And then there are other tools that we have, certainly alerts, so if you hit certain thresholds or, or if the system is threatened in any way, hopefully we have an alert on it and it'll trigger and we'll get the, basically a non-team to go and get the close line. So there are a lot of, I would say mostly it's automation and then there's this black art to it where certain scenarios just being in there, figure it out. I'll be around for a little bit longer if you want to just come talk to me.
Awesome. Well, thank you so much. If you is going to be on September 17th. We're doing the Science of Uber. If you have any questions, I will not shamelessly self-promote myself on Twitter anymore, as my colleague Ben liked to make fun of me for. But if you do work for Atlassian, can you raise your hand? If you're in here and you work for Atlassian, there's quite a few of us. And I heard quite a few of you had questions for us. So come find us if you have any questions. Come find me if you have any questions about community or Mary, and we're happy to answer them for you. Thanks again for coming, and hopefully we'll see you in September.